In this lecture, we'll start discussing one of the most common solution methods for linear programming, which is called the simplex method. But first, in order to start, we need to slightly modify the description of the problem that we are working with. We need to put it in the standard form. By putting the LP in the standard form, we will reduce it to a problem where we only have the equality constraints or equations and non-negativity constraints. Let's look at some inequality constraint in the form, say, x1 plus 2x2 plus 3x3 is less than or equal to 4. Okay, so this is a less than or equal to inequality. Obviously, for any feasible point, we'll have the left-hand side, which is less than or equal to the right-hand side. To convert this into equality, what we can do, we can add what we call a slack variable to the left-hand side. All right, so there may be some non-zero slack between right-hand side and left-hand side. And let's denote this slack by the variable s. And now, by adding this slack, we want to make sure that instead of the inequality, we'll have the equality constraint. S, the slack, is the difference between the right-hand side and the left-hand side. So S is 4 minus x1 minus 2x2 minus 3x3. All right, so this is the difference between the right-hand side and the left-hand side. If you think about this constraint as a resource constraint, for example, then the right-hand side represents the amount of resource available. So, and this slack variable gives you the amount of the resource that you are not using. Okay, so this is the difference between the available resource and the used resource given by this expression here. For any feasible solution, of course, this difference must be non-negative, right? So we have S is greater than or equal to 0. We didn't quite get rid of the inequality here. We just moved the inequality sign into a different place. So we have equation here now, the equality instead of the inequality, but now we have an additional variable and we have an additional inequality. S is greater than or equal to 0. In the standard form, we will allow the non-negativity constraints, and these are the only inequalities that we will have. So everything else will be in the equality form, and therefore we can operate with these equations as we are used to when we solve the linear systems. Similarly, if we consider the greater than or equal to constraints, say if I have something like this, x1 plus 3x2 plus 6x3 is greater than or equal to 5. So in this case, the left-hand side exceeds the right-hand side, and we can subtract this excess from the left-hand side. So in this case, we can talk about the excess variable, so E. So when we subtract this E, then we'll get the equality constraint instead of the inequality constraint. So in this case, the excess is given by the difference between the left-hand side and the right-hand side, right? So in this case, we'll have x1 plus 3x2 plus 6x3 minus 5. Okay, so this is our new variable E, and of course, E must be greater than or equal to 0. The same observations hold here. We didn't really get rid of the inequality, we just converted it into a different inequality for the new variable. So now we have the non-negativity constraint, but we converted the original inequality into an equality. LP in standard form has only equality and non-negativity constraints, as we said. Again, the way we convert the inequality constraints into equality constraints is as follows. Let's say if we have jth constraint, which is in the less than or equal to form, then we add a slack variable as j. So index j here will represent the constraint number. So jth constraint as j. So we have x1 plus 2x2 plus x3 less than or equal to 5, our original inequality constraint. Then we add the slack variable to the left. We have the equality constraint. So Sj is just the difference between the right-hand side and the left-hand side here. And of course, Sj must be non-negative. And then if our jth constraint is greater than or equal to constraint instead, then we subtract an excess variable, Ej, from the left-hand side. Assume that we had this inequality constraint to start with, then we subtract excess. We get the equality where the excess variable is given by this expression. And again, the excess variable must be non-negative. If we look at a complete LP here, where we maximize this objective subject to 4 less than or equal to inequality constraints, then we can use the same logic to convert it into a linear system. However, for this linear system, we will also have the non-negativity constraints for all the variables. So we introduce the slack variable S1 for the first constraint, S2 for the second, S3 for the third, S4 for the fourth. As a result, we convert all of these inequalities into equalities. For the first equation, we have x1 plus 3x2 plus x3 plus s1 is equal to 3, or the same is to say that s1, the slack variable, is given by 3 minus x1 minus 3x2 minus x3. We write this expression here. So this is our expression for the first slack variable. All right, so we do the same with the remaining slack variables. As a result, we have 4 equalities now. And then for the objective, we'll just use the variable z to represent the objective function. So z is just equal to the expression we had for the objective, so which was 5x1 plus 5x2 plus 3x3. In this standard form, we assume that all the variables are non-negative. All right, so our variables x1, x2, and x3 were non-negative to start with, and the way we introduce the slack requires that all of the slack variables are non-negative. So as a result, all the variables involved in this formulation, and now we have 7 variables. We have 3 original variables, and we have 4 slack variables. All 7 of the variables must be non-negative. So now this representation that we have here, we call this the dictionary form of the LP. And again, this representation, we have objective in row 0. So we start numbering the rows with 0, 1, 2, 3, 4. Okay, so this is row 0. And sometimes we'll also call it Z row. So now, with this representation, the problem of solving this original LP is reduced to the problem of solving this linear system subject to non-negativity constraints for all the variables. And also, we don't just need to find any solution to this system, but we need to find a solution such that Z here is as large as possible. All right, so we want to maximize this objective here. Okay, so now as soon as we have this representation for our solution algorithm, we don't really care which of the variables are the slack variables and which of the variables are the original variables. So what we'll do next, we'll just rename the slack variables into x's also. Okay, so we used x for the original variables, so we already used x1, x2, and x3 in the original formulation. So now instead of s1, we can use the next x, which will be x4. Then x5 will be used instead of s2, then x6 instead of s3, and x7 instead of s4. Okay, so this is just to show that we treat all these variables equally. And now this system has only x variables, and we need to find a solution to this system such that z is as large as possible, and all x's here are non-negative. Typically, the way we proceed with solving optimization problems, we start with some initial feasible solution, and then we try to gradually improve this solution step by step. We build a sequence of solutions such that each next solution is hopefully better, or at least no worse than the previous one. And we want this sequence to eventually converge to optimal solution. If we look at this dictionary here, how do we get an initial feasible solution from this dictionary? So one easy way to go in this case, by observing that all the numbers in this column are positive, we see that if we set x1, x2, and x3 all to 0, then this part here will disappear. The values for x4 will be 3, for x5 2, x6 is 4, and x7 is 2, and this will give us a feasible solution to our problem, because everything is non-negative as required. This is the worst possible feasible solution that you can come up with here, because you cannot really have a feasible solution with objective less than 0 for this problem, and by setting x1, x2, and x3 to 0, your z is equal to 0. Well, it's not necessarily a great solution for a maximization objective, but it is a feasible solution, all right? And a feasible solution is all we need to start our process. In fact, the way we got the feasible solution was also very straightforward, right? So we just said, okay, these variables that we have on the right, we just set them all to 0, and then the variables that we have on the left here, they'll just get their values automatically from this column right here. Okay, so very easy and straightforward way to get a feasible solution, right? So, but of course, we have to note that if some of these right-hand sides here were negative, then we wouldn't really get a feasible solution by setting all of this to 0, right? So, but for now, assume that we have all positive right-hand sides here. We will worry about negatives later, okay? So assuming that all of these are positive, by setting these variables to 0, we get a feasible solution to our system. This is what we call the initial feasible dictionary. Okay, so remember before we started using the term dictionary for this representation of the LP, and now we'll call it the feasible dictionary. Whenever by setting all the variables in the right-hand side to 0, we get a feasible solution, so we get a non-negative values for all the remaining variables. These variables that we have here on the left, remember we started by using the slack variables on the left, so these variables are the only variables that can be positive in this representation, right? So as soon as we set all the variables here to 0, these are the only variables that can be positive. And we'll call these variables the basic variables. We'll think of x4, x5, x6, and x7, so the variables that we use on the left as the variables that form the basis, and then all the remaining variables, they'll be called non-basic variables. So the non-basic variables are the ones that I set to 0. With this way of constructing a feasible solution, where I set all the non-basic variables to 0, we call it the basic feasible solution, so or BFS, corresponding to this dictionary. And the way our method will proceed, we will try to build a sequence of these basic feasible solutions, such that each next basic feasible solution is better, or at least no worse than the previous one, and in the end we want to obtain a basic feasible solution for which we can guarantee that it is optimal. At step 0, we have this dictionary. Our initial basic feasible solution is given by this solution here, so we just set all the non-basic variables to 0 and obtain the rest of the variable values. In particular, our objective value is 0. The question is, how do we obtain a better solution from the given solution? Let's look at the objective. So we look at 0. Let's think about how we can improve our objective. So let's look at each individual variable here. So right now, all the variables in the current solution are set to 0, so that's why our objective is currently 0. But we also know that our variables are all non-negative. So therefore, if I am to change the objective function value, I have to increase some of the variables. Okay, so I cannot decrease them, right? So because they're already at 0, if I decrease them, I'll get an infeasible solution. So they'll be less than 0. And then let's look at the coefficients for these variables. Let's see what happens if, say, I increase the variable x1 by 1 unit from 0 to 1. So if I increase the variable x1 from 0 to 1, then instead of 0 for this part, I'll have 5. And then let's keep x2 and x3 at 0 for now. Let's try to increase one variable at a time. If I increase x1 to 1, then my objective will become equal to 5, which is definitely better than 0 since we are maximizing. Let's see what happens to the remaining variables. Okay, so we agreed that we keep the other non-basic variables at 0, but what happens to the basic variables? So we'll have x4 will become 3 minus 1, which is 2. Then we'll have 2 plus 1, 3 for x5. x6 will become 4 minus 2 is 2. And x7, 2 minus 2, 0. All values we got for the basic variables, they are still non-negative, so this solution appears to be feasible. So therefore, we can make this increase. Let's see if we can also increase the objective value by increasing the value of x2 instead of x1. Okay, so now we assume that x1 and x3 are kept at 0, and for x2, say I want to increase x2 from 0 to 1. Okay, as a result, also the objective will increase by 5 units, which is exactly the coefficient for x2. Right, so let's look now at what happens to the basic variables. So we'll have x4 is now 3 minus 3 is 0, so it's still non-negative, so this is fine, right? Then x5 doesn't change, okay? So x5 remains at 2 as it was before. Then for x6, we'll have x6 is equal to 4 plus now x2 equal to 1. 4 plus 1 is 5, right? So x6 actually increased. And let's look now at x7. For x7, we have 2 minus 3. So, and we get actually negative 1. So we can see that the increase of x2 by 1 unit would be infeasible. So we cannot do that. Okay? Now, what we have seen from this exercise here is that we can increase the objective by trying to increase the values of some of the variables that are included in the objective here. And the only variables included, because of the way we describe the LP now with this dictionary form, the only variables through which we express our objective and the basic variables are the non-basic variables. Okay, so the objective depends now only on the non-basic variables. And by looking at the non-basic variables with positive coefficients, we can actually increase the objective. So if the coefficient was negative here, so let's say if I had minus 5 here, right? Then because my x1 is currently equal to 0, and the only change I can make to x1 is to increase it. So if I increased x1, my objective would actually decrease if I had minus here. So therefore, it doesn't make any sense for me to try to increase the variables with negative coefficients. All right. So, but whenever we have a variable with a positive coefficient in the objective, it means that there is a potential for increase, and we should try to use this to improve our objective function value. So we showed this by looking at the first two variables, but the same is with the third variable. I could try to improve the objective also by increasing x3 from 0 to something positive. Let's say if I set x3 equal to 1, like I did with x1 and x2, then my objective would change from 0 to 3. Then x4 would change from 3 to 2. Then x5 would become actually minus 1. So we see that this would not be feasible to increase x3 by 1 unit. But let's say I could increase it by 0.5, right? So by 1/2. So if I increased x3 by 1/2, then I would have 3/2 in the objective, so which is better than 0 again, right? So then x4 would be 3 minus 1/2, so it would be 2.5. Then x5 would be 2 minus 3 halves, which would give me 1 half, right? So which is greater than 0, so it's good. X6 would be 4 minus 2 times 0.5, so it would give me 3. Finally, X7 would be 2 plus 1 half, it would be 2.5. Even though I could not increase X2 or X3 by 1 unit, there is some amount by which I can increase each of these variables one at a time, such that the objective will go up and I still get a feasible solution. But as we see from the examples, the amount by which we can increase each variable is typically limited, right? So you cannot increase it as much as you wish. And of course, if you were able to do it within the feasible region, then this would mean that your problem is actually unbounded, right? So if I had all pluses in all of these constraints, then clearly, I can keep X2 and X3 at 0, and then I can increase X1 to plus infinity. I'll still stay in the feasible region because I only increase the values of all these variables, so they still remain non-negative, and this would increase my objective to plus infinity. So clearly the problem would not have an optimal solution. It's an unbounded problem. But whenever I have some minuses here, like I have for X1 in the constraints, the amount by which I can increase X1 is bounded by some value. We saw that when we increase X1 by 1, then we have all the non-negative values, and in particular X7 will become 0, right? So therefore, if I try to increase X1 by something greater than 1, I'll get an infeasible solution. All right, so 1 seems to be the maximum by which I can increase X1 here. So how did we determine this? Obviously, from here, I cannot increase X1 by more than 3, right? So I would get a negative value. Then what's the largest increase I can have from the second equation? Because I have a positive coefficient for X1 here, I can increase X1 as much as I wish, and this will not violate the second constraint. We don't really care about the second constraint when we increase X1 because we have a plus here. So, okay, so let's just skip the second constraint. Let's look at the third constraint now. So we have 4 minus 2X1, so this is the part I need to focus on, right? How much can I increase X1? So I can increase it as much as I wish, as long as 4 minus 2X1 remains non-negative. Okay, so and from here, by solving this inequality, I can actually see that this is true if and only if X1 is less than or equal to 4 divided by 2, which is 2, right? So I can see that the largest amount by which I can increase X1 for this constraint is given by 2, which is the ratio of this value here by this value here. So it was 4 by 2. Therefore, the largest increase is given by this ratio of 4 divided by 2, which is 2. So similarly, for the last constraint, again, if I try to determine the highest possible increase such that the slack is still non-negative, I need to divide 2 by 2 here, so the ratio I get is 1. So we saw now that as I try to increase X1 for the first slack variable to still be non-negative, I cannot increase X1 by more than 3. If you represent it as a ratio also, it was 3 by 1, right? So the second equation doesn't provide any restriction to us because the coefficient was positive, right? From the third equation, we see that the increase cannot be greater than 2, and from the fourth equation, it cannot be greater than 1. X1 is less than or equal to 3 from the first equation, X1 less than or equal to 2 from the second, and X1 is less than or equal to 1 from the fourth. Because we want all of the equations to be satisfied, so we want to make sure that all of the basic variables still remain non-negative. This is only possible when I select the smallest of these ratios, right? So in this case, the smallest ratio is 1. Okay, So now, what we did here to determine the highest possible increase for x1 was what we call the ratio test, or the minimum ratio test. How do we perform this ratio test? It was very simple, right? So we focused on the constraints where x1 had negative coefficients here in the dictionary. What we did next, we just looked at the ratios of the constants here to the coefficient of x1 that we have in the column corresponding to x1, right? So whenever we had a negative coefficient for x1, we divided the corresponding constant from the corresponding constraint by the absolute value of this coefficient for x1, right? So 4 by 2, and then we had 2 by 2 here. Wherever this ratio is the smallest, the row that corresponds to this smallest ratio, we'll call it the winner of the ratio test. So in this case, the winner was the row corresponding to x7. Therefore, this is the row that determines the highest possible increase for my x1. All right, so the ratio test determines how much we can increase the variable that we selected for increase, right? But now, what does it mean for our dictionaries and our basic feasible solutions? So remember our agreement, so we said that we always set all the non-basic variables to 0, and this way we get the basic feasible solution. When we decided to increase the variable x1 here, now it will be non-zero, right? So when we increase it from 0 to 1, it is greater than 0. Now it violates our agreement that all the non-basic variables must be 0, right? So in other words, x1, after we increase it, is not a non-basic variable anymore. So it turns into a basic variable. The other way to say it is that x1 enters the basis, and we'll call x1 the entering variable. Okay? If there is an entering variable, then we should have some leaving variable that will leave the basis. So which variable will it be? So we saw that the row that won the ratio test has the basic variable that used to be equal to 2, right? So but after we increase x1 to 1, it will turn into 0. So from 2 it will become 0. So therefore x7 appears to be a natural candidate to leave the basis, so we can make x7 the non-basic variable now and make the swap, you know, so x1 will become basic, x7 will become non-basic, and then our agreement about setting all the non-basic variables to 0 and then just getting the values for the basic variables will still hold, okay? So this describes essentially the step of the algorithm that we are discussing. Okay, so on every step, what we'll do, we'll determine the entering variable, the variable that will enter the basis, and this will be the variable that has the potential to increase our objective, so which means that it must be with a positive coefficient in the objective. And then as a result of increase in the value of the entering variable, the winner of the ratio test will turn into 0, and we'll call this variable the leaving variable. So it will leave the basis and will become a non-basic variable. All right, so now what we need to do, we need to update our dictionary, make sure that we still have the same rule where, you know, all the basic variables are kept on the left, and then all the non-basic variables are kept on the right. So we decided that we select x1 as the entering variable. Okay, so and typically we can select any variable that has a positive coefficient in the 0 as our entering variable, and it makes sense in many cases to pick a variable that has the highest positive coefficient in the objective, because this corresponds to the highest rate of increase in the objective with 1 unit of increase in the variable value, right? So we selected x1 as the entering variable. We'll also call it the pivot variable, and the column corresponding to x1 in the dictionary we'll call it the pivot column. So the next thing we've done, we looked at the ratios, right? So for the first constraint we had the ratio was 3 to 1. The second constraint was ignored because we had a positive coefficient for x1. The third constraint gave us the ratio of 4 to 2, which is 2. And the fourth constraint gave us 2 to 2, which is 1, right? So we saw that this is the smallest ratio we get. So this is the winning row for the ratio test. And we'll call it also the pivot row. All right, so we found the pivot row. And then the way we will exchange x1 and x7 as basic and non-basic variables will be as follows. So we'll just look at the pivot row. Pivot row is the only row which has the variable x7 among all the rows, right? So now x7 will become non-basic variable, x1 will become the basic variable, so we need to swap x1 and x7, for which we just need to express x1 through x7 and the other non-basic variables. This is easy to do from this row. We just move x1 to the left and then divide everything by 2. So we'll have x1 is 1 minus 3/2 x2 plus 1/2 x3 minus 1/2 x7. All right, so we got the expression for x1. Now, because x1 becomes a basic variable, we need to eliminate it from each row from the right-hand side, okay? And we can easily do it by just substituting this expression for x1 in every row. Okay, so let's start doing this with the objective. 5x1 plus 5x2 plus 3x3. Let's replace x1 with the expression for x1 that we have from here. So we'll have 5, instead of x1 we are now writing 1 minus 3/2 x2 plus 1/2 x3 minus 1/2 x7, and the other two terms are still remaining, 5x2 and 3x3. Now the new expression for z we just get by computing the corresponding coefficients for all the variables, and we'll have 5. Then the coefficient for x2 would be minus 15/2 from this part, and then 5 from this part, so 5 is 10/2, right? So minus 15/2 plus 10/2 gives us minus 5/2 x2. All right, so now the coefficient for x3 will be 5/2 from here and 6/2 from here. So 5 plus 6 will be 11/2 x3. All right, and finally the coefficient for x7 will be minus 5/2. All right, so we got the new expression for z, and we will put it in our new z row. Okay, so z is 5 minus 5/2 x2, then plus 11/2 x3, and then minus 5/2 x7. Okay, so let me draw the line here between z row and the constraint rows. All right, so now we can get rid of this part here. So next, the first constraint. Okay, so the expression for x4, now we need to eliminate x1 from that expression. So let's do this. x4 is 3, and then minus x1. So instead of x1, again, we write the expression for x1 that we have here. So it will be 1 minus 3/2 x2 plus 1/2 x3 and minus 1/2 x7. So it was 3 minus x1 minus 3x2 minus x3. Okay, so we have 2, and then the coefficient for x2 is 3/2, and then minus 3. So 3/2 minus 6/2 will be minus 3/2 x2. Then the coefficient for x3 is minus 1/2 from here and minus 1 from here. Again, minus 3/2 x3. And the coefficient for x7 will be 1/2. Okay, so now we are ready to write the expression for x4. It is 2 minus 3/2 x2 minus 3/2 x3 plus 1/2 x7. All right, so let's move on to the next constraint. So in the next constraint we have x5. So the expression for x5 is 2 and then plus x1, and again we substitute our expression for x1, which is 1 minus 3/2 x2 plus 1/2 x3 minus 1/2 x7, and then there is no x2, and minus 3x3. So which is 3 minus 3/2 x2. Then what's the coefficient for x3? It's 1/2 from here and minus 6/2 from here. So minus 5/2 x3, and then minus 1/2 x7. All right, so you write x5 is given by 3 minus 3/2 x2 minus 5/2 x3 and minus 1/2 x7. So let's now find the expression for x6, and then we'll be done. For x6 we have 4 minus 2 times x1, where x1 is 1 minus 3/2 x2 plus 1/2 x3 minus 1/2 x7. Then we have plus x2 and minus 2x3. Which is 2. Then the coefficient for x2 would be minus 2 times minus 3/2 is 3 from here and 1 from here. 4 x2. Then the coefficient for x3 is minus 1 here and minus 2 here, so minus 3x3. And the coefficient for x7 is minus 2 times minus 1/2, so which is 1. Okay. All right, so let's write this here. So we have x6 is 2 plus 4x2 minus 3x3 plus x7, and we are done. So we finished computing the new dictionary. We can see that in this dictionary the variable that was previously non-basic, which is x1, is now basic. Okay, so now x1 is among the basic variables, and then the x7 variable, which used to be basic, is now among the non-basic variables. All right, so and again, to get the corresponding basic feasible solution, all we need to do is to set the non-basic variables to 0. So we set x2, x3, and x7 to 0. And then we get the values for the rest of the variables by just looking at this column here. So x1 will be 1, x4 will be 2, x5 is 3, and x6 is 2. Okay, so and the corresponding value of the objective z is given here, so it's 5. Okay, so this is our new basic feasible solution. And of course, the list of basic variables, our basis, is given by first, fourth, fifth, and sixth variable, and then the non-basis is given by the second, the third, and the seventh variable. So we see that we made one step, which we call the pivot. We made this pivot, and as a result, we exchanged two variables from the basic and non-basic list, right? So one basic variable became non-basic, one non-basic became basic. But what's most important is that as a result of this swap, our objective increased from 0 to 5. Okay, so the current basic feasible solution is better than the previous one because it has the higher objective value. All right. So now, by looking at this dictionary, we see that we still have the potential to increase the objective even further. How can we increase the objective from 5 to something greater? So let's look again at the objective here. As always, the objective is expressed as a function of non-basic variables only. If we want to increase the objective, we need to look at the coefficients for the non-basic variables in the objective, right? Let's look at x2. Right now, x2, as well as all the other non-basic variables, is kept at 0. If we change x2, this may only result in the decrease in the objective because we have a negative coefficient, right? So the same is with x7. However, for x3, we have a positive coefficient, and we can still try to increase x3. As a result, we may get a better objective value. So let's try to do that. All right. So now x3 will be the entering variable, right? So because this is the only variable with the positive coefficient in the objective, the next thing we do, we perform the ratio test. Okay, so let's look at the first row. So remember, we ignore all the rows where the coefficient for x3 will be positive. The coefficient is positive, so we ignore the first row. For the second row, the ratio will be 2 divided by 3 halves, so which is 4/3. For the third constraint, we'll have 3 divided by 5 halves. And finally, for the last row, we'll have 2 divided by 3, 2/3. And the last row wins the ratio test because it gives us the smallest value, right? The row corresponding to x6 will be the pivot row. Now we need to perform the pivot. We move x3 to the left and divide everything by 3, right? So because the coefficient was -3 here. So we'll have 2/3 plus 4/3 x2, then minus 1/3 x6, and plus 1/3 x7. Okay, so this is our expression for x3. So and note that in the next basic feasible solution that we'll get after we perform the pivot, the value for x3 will be equal to 2/3, right? So because we'll set all the non-basic variables to 0, and we'll get 2/3, which is exactly the minimum ratio value. If, let's say, we want to find out the values for all other basic variables after we perform the pivot and the value of the objective after we perform the pivot, we don't really need to compute everything here. We can actually get this information by just looking at the ratio, the constant part for the corresponding constraint, and the coefficient for the entering variable, right? So because, for example, if I look at x1, x1 is 1 minus 3/2 x2 plus 1/2, and then for x3 we'll write the expression that we just got, so which will be 2/3 plus 4/3 x2 minus 1/3 x6 and plus 1/3 x7 minus 1/2 x7. So this is what we get from here. Now let's just compute the constant part, because this is what will be the new value for this basic variable after we complete the pivot. To compute the new value for this basic variable, we just need to focus on three parts. One was the previous value that we had, right? So then 1/2 was the coefficient for the entering variable in this row, and then 2/3 was actually this value here, which is the same as the minimum ratio value, right? So it's 2/3. So we see that in order to compute the new value for this basic variable x1, all we need to do is to look at this value and then plus the coefficient for the entering variable multiplied by the minimum ratio. And in this case it is 1 plus 1/2 times 2/3, and then plus the expression depending on x, which we don't care about for now. So it will be 1 plus 1/3, which is 4/3. We can see that for the new basic feasible solution, the value of x1 will be 4/3, therefore. The new BFS, x1 is 4/3. Similarly, we can compute the new values for x4. It will also be 2, so this value here, minus 3/2 and multiplied by the minimum ratio, which is 2/3, right? So for x4, it will be 2 minus 3/2 times 2/3, which is 1. For x5, using the same logic, we'll have 3 minus 5/2 multiplied by 2/3, right? So 3 minus 5/2 times 2/3, 4/3, okay? For x3, the value was equal to the minimum ratio, so which is 2/3. The rest of the variables will be equal to 0. The new value of z will be given also by the old value of z plus 11/2 times 2/3, right? So it will be 5 plus 11/2 multiplied by 2/3. This gives us 26/3. So this was just to illustrate how we can get the new basic feasible solution without really computing the full dictionary to compute all the remaining parameters. So we just use exactly the same steps, right? So we already expressed x3 through the rest of the variables. Then we'll plug in the expression for x3 instead of x3 in all of the remaining constraints and the objective role. And as a result, we'll get the new dictionary, okay? So we'll not go over all these details here. Instead, we will move back to the slides. So here we have the step 1 feasible dictionary, which is exactly the dictionary that we obtained after we performed the first pivot. We saw that x3 was the entering variable, x6 was the leaving variable, and after performing the pivot, we will get the following dictionary, okay? So this is after we do all the computations, okay? And you may want to try this to make sure that you follow the steps correctly. Okay, so after you do all the computations, this is what you're supposed to get. So our new list of basic variables would be x3, x1, x4, x5. Non-basic variables are x2, x7, x6. We see that there is only one variable that has a positive coefficient in the objective, so x2 will be the entering variable. Now we perform the ratio test, okay? So for the first row, the coefficient is positive, we ignore it. For the second row, it's 4/3 divided by 5/6, which gives us 24/15, right? For the next row, it will be 1 divided by 7/2, so which is 2/7. And finally, for the last row, we'll have 4/3 divided by 29/6, so which will give us 8/29, I believe. The smallest among these values is 8/29, so this is the ratio test winner. So this is our pivot row. x5 will be the leaving variable. From the pivot row, of course, we would express x2 through x5, and then we would plug in the expression for x2 instead of x2 in every other row. And as a result, this is what we get. So you see now x5 became a non-basic variable, and then our basic variables are given by x2, x3, x1, and x4. Now in this dictionary, all the coefficients for all the non-basic variables in the objective are in fact negative. Therefore, we can claim that the solution that we obtained here is actually an optimal solution to our problem. All right, so why can we claim this? Let's look at the representation that we have for our LP. The only variables that appear in the objective are x7, x6, and x5, and all of them appear in the objective with negative coefficients. The system that we have here, the only manipulations we have done to original dictionary and all the other consecutive dictionaries that we got at every step were what we call the elementary row operations. The system that we get in the process, it is always equivalent to the previous system that we had, right? So this system that we have is equivalent to the original dictionary. We swapped the basic and non-basic variables. We expressed this set of 4 variables through the remaining set of 3 variables, but it is essentially the same system, right? Now, the objective in this representation depends only on the 3 variables, and we see that all of them are included with the negative coefficient, right? Therefore, the best we can do for the value of z here is just to set all these variables to 0. All right, so if we set them to something positive, then the objective will obviously be smaller than 10. The highest objective we can get would be 10. All right, so by setting all of these variables to 0. Therefore, because of the way we represented our LP now, it is very obvious that we cannot do better than 10 for the objective. At the same time, by setting all the non-basic variables to 0, we do get 10 in the objective value, and this is the best we can do, and therefore this solution that we get is the optimal solution. So this basic feasible solution that we got is obviously the optimal solution for our problem, and we can report it as follows. So when we report the solution, we can actually ignore all the slack variables because they were not a part of the original problem formulation, so we don't really need to report them in the final solution. Okay, so let's ignore x4, x5, x6, and x7 and just write down the values for x1, x2, and x3, and the optimal objective value is 10. So this is our optimal solution, so we solved our first LP.